Hello, good day everyone. So, soft pneumatic actuators are a really important factor in any soft robotic system. Therefore, we decided to do research on soft pneumatic actuators because this industry has a lot of potential in the future. Therefore, today I will present our research on estimating the shape of soft pneumatic actuators using active vibroacoustic sensing. And I am Kazumi Chandrasiri. So soft pneumatic actuators are used in a broad range of fields, mainly in soft robotics. They are flexible but strong and can be used safely during human and robot interactions. However, in order to increase their functionality and to control these actuators efficiently, a reliable sensing approach is necessary. In the past, many research were conducted to sense soft pneumatic actuators. Embedded sensors such as flex sensors, thermistors, and optical waveguides were used to sense contact targets and shape. In recent years, acoustic sensing was also used on soft pneumatic actuators. In order to understand the sensing of soft pneumatic actuators using acoustic sensing, I would like to explain further related research. Out of the many, research such as soft pneumatic actuator sensing has been performed with active and passive acoustics. Here, the vibrations were used to sense the contact location, contact force, and contact materials on soft pneumatic actuators. Also, acoustic sensing is used for length estimation by employing the resonance of the vibration inside extensible actuators. However, in all of these research, sensing devices are embedded in the actuator, and the sensing method has limited applicability on other types of actuators. Therefore, in our research, the aim is to create a versatile shape estimation method for soft pneumatic actuators using active vibroacoustic sensing. So we propose a method that can be used among different actuators without significant changes in the sensing devices and the estimation methodology. So our approach is different to that of many typical approaches in the past. We avoid the embedding of sensors inside the actuator, and instead we attach our sensing devices externally onto the actuator. So this avoids complex fabrication process of actuators and specific sensor layouts for various actuators and applications. The propagated vibrations along these actuators are used to estimate their shape. In our research, the bending angle of a Pneu-Nets actuator and the nominal length estimation of a PMA was done. So let me take you through the results of our proposed method. We were able to estimate the bending angle of a Pneu-Nets actuator. As you can see, angles between 0 to 110 degrees were estimated. So due to the limited presentation time, in this video, I have included a combination of short clips, a few sections of the estimation between 0 and 110 degrees. The bending angle estimation was possible with an average error of approximately 5 degrees. We also implemented the estimation methodology on a pneumatic muscle actuator, or a PMA, to prove the versatility of this proposed method. The maximum contraction of this particular actuator is only 20 millimeters, which is 2 centimeters and very small. Therefore, we considered a contraction of 10 millimeters to safely contract these actuators numerous times during our experiments without risking any damage to it. And the length estimation was possible with an average error of about 0.3 millimeters. Let me move on to the implementation process. We used a simple system configuration for acoustic sensing. This consists of a control board to control the air pressure inside the actuators, a contact microphone, and an oscillator as our sensing devices attached to the origin of the actuator. As you can see in these minifigures, the same contact microphone and oscillators are used in both the actuators. Next, this slide briefly depicts the flow of our research. First, we emit a sweep signal onto the actuator and acquire the propagated vibration throughout the actuator. We then pre-process this acquired data by creating spectrograms that will be used as input for our machine learning model based on convolutional neural networks for shape estimation. At the pre-processing stage, the vibration acquired is amplified by 40 decibel. This is due to considerable attenuation of vibration during the propagation on actuators. Amplitude spectrums of 50 millisecond frames are created. And by fast Fourier transformation, these amplitude spectrums are used to obtain spectrograms, each with a length of 50 milliseconds. The resolution of a spectrogram is 300 by 1 pixel. So before moving on to main experiments, we confirm the feasibility of vibration on actuators, whether they have any characteristics or not. First figure here shows the spectrogram when vibrations were acquired from Pneu-Nets. And the second figure shows the vibration from a PMA actuator. So as you can see, the vibration propagation in both the actuators are very different and shows the features of the acquired vibration. We understood that the characteristics in the frequency domain changes along with the change in shape of the actuators. We used a data-driven approach for our estimation. A CNN model was created for two-dimensional input, as shown in this figure. The architecture consists of 3 convolutional layers, 3 max pooling layers, and 3 fully connected layers. And the input is an image of 300 by 1 pixel. Next, I would like to present the evaluations of our proposed method. Several evaluations were done for this proposed method. Experiments were performed for Pneu-Nets actuator and PMA under free motion without any external disturbances such as contact or any external noises. We used incremental actuation and contraction for creating estimation models for Pneu-Nets and PMA. We also performed additional experiments to test the estimation in continuous motion of a Pneu-Net. And changes in machine learning algorithms were tested to prove further versatility. This slide explains the data distribution during the evaluation experiments. The Pneu-Nets data consists of data from 23 different angles, and each angle has 1,000 data. Therefore, one dataset consists of 23,000 spectrograms. As for the PMA, 3 contracted lengths were considered, and 2,000 data per length were acquired. Therefore, one dataset consists of 6,000 spectrograms. The data distribution during training is 80%, and evaluation is 20%. 2 separate models were created for Pneu-Nets and PMA using the acquired data in various experimental scenarios. So the first evaluation is free motion of Pneu-Nets from 0 to 110 degrees with 5 degree increments. Therefore, 23 different angles were acquired. The estimation was successful with a high accuracy. The visual results of the estimation were shown in the first video at the start of the presentation, and the same results numerically are shown in this graph. Next, continuous actuation using the estimation model created with the incremental data was performed. An acceptable estimation was possible without changing the estimation model. So we used the same incremental estimation model from our previous experiment to estimate continuous actuation from 0 to 110. And the results are shown in this graph. To further prove the versatility of this proposed method, shape estimation was done in a PMA. The nominal length after contraction was estimated. Here, increments of 0.5 millimeters were done, and the maximum contraction was 10 millimeters. The results show that nominal length can be estimated using the proposed method. The real-time estimation was shown in our second video at the start of this presentation, and this graph consists of the same results numerically. Lastly, an evaluation of machine learning techniques were done. A model based on CNN, as we introduced earlier, would require a large amount of training data. However, we considered a situation where the amount of data is low and employing a simple machine learning technique depending on the application. For this, we considered the Pneu-Nets actuator as our main testbed due to varied angles. So using these data, we created a simple neural network model, a support vector regression model, and a one-dimensional convolutional neural networks model, which used power spectrum data of one dimension as input. And the bending angle estimation was possible in all of the above techniques. However, the estimation error was higher than 2D CNN model. So even though we cannot for sure say that the estimation accuracy is high, depending on the application, we could conclude that the estimation accuracy is acceptable and that a simple machine learning technique can also be selected. Therefore, this proposed method is still feasible for shape estimation. So this concludes the evaluation of our proposed method. In every methodology, there are limitations. In our research, the annotation of data was cumbersome. In robotic systems, an automatic data acquisition system would be ideal. However, in our research, data acquisition system involved human intervention. Therefore, the time taken to acquire data is high, and also there is a risk of acquiring corrupt data if we were not careful. In addition, this research mainly focuses on soft pneumatic actuators. Therefore, other types, such as tendon-driven hard actuators, are not yet tested. Finally, the angle estimation of a continuously actuated Pneu-Nets did not have a very good accuracy. We used an estimation model created with incremental actuation data. So one of the reasons could be that the frequency dominant features for close angle values could be similar. For example, the characteristics at angle 10 and angle 11 could be very similar. So as a solution, creating a separate estimation model trained with only continuous actuation data would increase the estimation accuracy. However, these areas are yet to be proven and experimented. I would like to conclude this presentation with a summary of our research. We used active vibroacoustic sensing on 2 soft pneumatic actuators. The estimation targets were bending angle of a Pneu-Net and the nominal length of a PMA. Both estimations were evaluated and performed in real time. We also used several machine learning techniques to test our methodology. All of the above proved that our method is more versatile and can be used in different actuators. As for our future works, we would like to create a robotic data acquisition system to speed up the entire process. Furthermore, we will implement this method on various actuators other than the PMA and Pneu-Nets that has different estimation targets. And also not just during free motion, but also during more realistic scenarios, such as sensing and environmental variations, including contact events on the actuators during their applications. Thank you for your support by listening to this research presentation. I look forward to presenting at the live spotlight session. So please give us your comments and questions that will help us improve the research.